This is Yawei Hui at the Computer Science and Mathematics Division. I collaborated with Dr. Yaohua Liu at the Condensed Matter Division at SNS and tried to locate, identify, and track the movement of atoms imaged in a series of STEM images. In the first task, we used the classic blob detection algorithm in computer vision to locate the atom centers in each frame. In order to increase the accuracy of the detection algorithm, we pre-treated the images with isotropic blurring. We have noticed, however, other denoising processes such as image tychography could be applied in this situation to better the final outputs. In the core of our approach for center detection, we calculated the second-order partial derivatives of intensities on an image in form of a Hessian matrix. The maximum of the Hessian determinants were used to pick the possible intensity centers according to the atom positions. The final results of the center detection are shown as a still image for the first frame and a GIF animation for all 49 frames. In the second and third tasks, we tried to track the movement of the atom centers, which appeared in all 49 image frames. The results are shown as an animated tracking map for all trackable atom centers. The approach used here was simply to evaluate the relative movement of atom centers in adjacent frames within their nearest neighborhoods. The definition of the nearest neighborhood is based on the statistics of the pairwise distance of all centers between two adjacent frames. In this specific case, the likelihood of an atom moving within its nearest neighborhood is localized in an annulus of 20 to 30 pixels. We simply took 15 pixels as the maximum radius one atom could move from its previous center without losing its track. We consider the biggest challenge comes from the last task, which is to identify all atom centers as either molybdenum or selenium. Lack of further information, we had to rely on either their relative intensity differences or the overall lattice orientation. After calculating the nearest neighbor distances at a fixed radius, we picked atom centers which have 2, 3, or 4 neighbors and compared the intensity at the center with the average intensity of neighbors. Due to the fact that selenium atoms are 8% brighter than the molybdenum, we marked the atom centers selenium with relatively higher intensities compared to its neighbor's mean, or otherwise, molybdenum. In the still image of the first frame on the left, we marked the identities of molybdenum and selenium atoms as triangles and dots, respectively. On the right, we showed the tracking of all identified atom centers. At the end, we thank the organizer of the SMC Conference Data Challenge for such a valuable opportunity and hope this effort could be furthered to bring more domain experts together on solving the diverse data challenge faced in their everyday lives. Thank you.